Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our or our second day of notes from Chapter 5, dealing with understanding how light behaves like a wave and then how light behaves like a particle. So, basic on the wave nature of light, remember that we talked about electromagnetic radiation in day 1, and we said that all electromagnetic radiation moves at the same speed, which is the speed of light, 3.00 times 10 to the 8th meters per second. Now, that's represented by the symbol c, and you may have seen that C before and just not realize it. Einstein's E equals mc squared equation has the speed of light in it, but that's not how we're going to use the speed of light in this particular case. Now, we know that the speed of light is the product of the wavelength and the frequency. And remember, the symbol for wavelength is the Greek symbol lambda, which looks kind of like a weird looking giraffe. And the symbol for frequency is a crooked looking V, which represents nu. So wavelength times frequency actually equals the speed of light. Now, the speed of light is a constant. So that means when the frequency and the wavelength vary, they vary in a very specific way with each other. So as a set of two variables that are inversely proportional based upon the fact that they multiply to a constant, when wavelength gets bigger, that means frequency has to get smaller for them to equal the same constant. And vice versa, when frequency gets bigger, that means wavelength has to get smaller. So they always multiply to the same constant. So if we know one, we can calculate the other. Now, we said just a second ago that wavelength and frequency are inversely proportional to each other. So if we have a red and purple wavelength of light, now picture this as a 1-second snapshot of light. Now, I know this is not to scale, so to speak, but at least it gets us to the idea of understanding how when wavelength is getting bigger, frequency is getting smaller. So from here to here is one wave cycle, one up and down propagation. So if I look at the top set of waves, I have 1, 2, 3, 4 wave cycles. Now, if this was a picture in 1 second, that would mean I would have 4 waves every second, or 4 hertz would be my frequency. Now, if you look at the purple colored waves on the bottom, there's one wave cycle. And in the purple colored waves, I have 1, 2, 3, 4, 5, 6, 7 wave cycles here. So in this particular case, I've got a frequency of 7 waves per second, which would be 7 hertz. Now notice the purple ones at the bottom have a higher frequency. Well, notice the wavelength relationship. This would be the length of a wave from here to here, which is easier measured from crest to crest. And then on top, that's my crest to crest wavelength. Notice that even though the one on top had a longer wavelength, it had a smaller frequency. And the one on the bottom had a smaller wavelength, but it had a larger frequency. Well, remember, we just said a second ago that these two things are inversely proportional. So this is exactly what I would expect to see. As my wavelength is getting shorter, my frequency should be getting bigger. Now, what is a typical math problem look like related to this equation? So what's the wavelength of a microwave having a frequency of 3.44 times 10 to the 9th hertz? So I have microwave electromagnetic radiation, and as electromagnetic radiation, I know this relationship is true. Wavelength times frequency has to equal the constant, which is the speed of light. Now, the first thing I always want you to do with these is to manipulate and solve them before you plug in the numbers. And we're going to be consistent with that all year long. So if I want to solve for, in this case, the wavelength, that means I need to isolate the wavelength. And remember, we talked about this before. That means first you have to get it on top, and second you have to get it alone. Don't just isolate and get it alone first. You have to get it on top and then get it alone. Well, it's already on top, so that part is solved. So how do I get it alone? Well, if I divide both sides by the frequency, then the frequencies on the right would cancel, and I'd be left with wavelength equals the speed of light over nu. And that's exactly what my equation looks like. So when I solve the top equation for what I'm supposed to find, which would be wavelength, lambda, lambda would equal c divided by nu. So one of the things I want you to do in homework is I want you to show me the top equation. I know it's this equation, and then solve that equation for the selected variable. Then and only then can you plug in the numbers. Now in this case, my speed of light, right out of notes, 3.00 times 10 to the 8th meters per second. And my frequency was given as 3.44 times 10 to the 9th hertz. Now remember, a hertz is the same as an inverse second. And as inverse seconds, it's easier to see how the units cancel here. So in my calculator, I would take and divide the two. and to three significant digits, I get 8.72 times 10 to the negative second. Now, why do I get units of meters? Well, I've got inverse seconds on top and inverse seconds on bottom. They're going to cancel each other. What I'm going to be left with is meters. So that makes sense that a wavelength would be a unit of length, the meter. Here's another problem. A helium neon laser emits of light with a wavelength of 633 nanometers. That's pretty common for you to sometimes see things in nanometers because most of our visible spectrum, we get numbers that are normal when we're in nanometers. Not very normal when we look at what it actually is in meters. So don't let it throw you if you see the number in nanometers. You'll notice I also give you the number in meters, and that's the one you got to use. So what would be the frequency of this light? Well, I know my speed of light equation, C equals lambda nu. So in this case, I'm now going to solve for the frequency. So I want to divide both sides by lambda. Lambdas would cancel. And remember, the reason I'm dividing both sides is what I do to the left, I have to do the right and vice versa. And I'll be left with frequency alone. So this is my base equation, and solve for variables. Nu is going to equal C divided by lambda. And once again, now I'm ready to plug in my numbers. But remember, in order for units to cancel, if my speed of light is meters and seconds, I can't use nanometers. I have to use my value in meters. So I'm going to use 6.33 times 10 to the negative 7th on the bottom, and that's why I use that one. Now in this case, you'll notice that my meters are going to cancel, and what I'm going to be left with is 1 over seconds, which is the same as a hertz. And to three significant digits, my calculator would give me 4.74 times 10 to the 14th hertz. And make sure you actually do these in a calculator, because I'm telling you what the answer is supposed to be. Make sure you're hitting the right buttons. Remember, it's that little EE button, and you never hit the times or the 10. So make sure you're using the number properly and you can get the right answer. And remember, hertz is the same as 1 over s or s to the negative 1. All of these are perfectly fine ways to express your units here. It's just usually you see it written in hertz. Now, not only does light act like a wave, which we just spent some time looking at a mathematical relationship of lights acting, or which is an energy form acting like a wave, eventually scientists realized that light sometimes also behaves like a particle. And now we're getting into what is known as quantum physics. So for years, scientists had treated light as an energy form, and it behaves as we describe energy forms, which means wave-like properties. And matter is a particle, and matter should be explained by particle properties. Well, eventually scientists realized light was doing some things that wave properties couldn't explain. So Planck and Einstein and others came up with a way to treat light as if it were a particle. And this was a huge shift in science, which in the end was really important for understanding of the electron. So while considering light as a wave does much to explain its everyday behavior, it doesn't explain adequately all of the different things we knew about light. The fact that when you have a metal and it starts to glow, the fact that it glows with all of the colors of the rainbow, scientists couldn't explain that by wave behavior. And then something that Einstein was studying, which was known as the photoelectric effect, which is something that gets harnessed in most of our solar calculators that you use. So in both of these cases, we really couldn't explain why it was doing what it was doing if we treated light like it was a wave. And we found out sometimes light acts as if it's a little bundle or a photon. So in 1900, Max Planck began searching for an explanation when he was studying the light emitted from heated objects. And he found that matter could gain or lose energy only in small, specific amounts. So specific quantities, he called that a quanta. So a quantum or a quanta is a specific quantity of energy. So quantum is the minimum amount of energy that can be gained or lost by an atom in these cases where it's gaining and losing energy. So it can only absorb specific energies of uh, wavelength, or excuse me, it can only absorb specific energies, the piece of matter itself, and when the matter glowed, it would emit at specific energies as well. And what he found out was that this was light acting like a particle. Now, Planck found that the energy of a quantum, or what we call a photon of energy, is directly proportional to the frequency in this equation. Energy equals h, which is called Planck's constant, times nu. So this shows the relationship between the frequency and energy of a particle or bundle of light known as a photon. And remember, this is actually calculating the energy of one single photon. So we're talking about one photon, so it should be a very small energy. Now, Planck's constant is 6.626 times 10 to the negative 4th joules times seconds. And that unit is going to be very important for getting the right units when we do our calculations here. And remember, joule is something we talked about earlier in the year, but it's been a while. It's our unit for energy. So whenever you see joules, you know we're talking about energy. So in this case, it would be joules times seconds. Now they're directly proportional because unlike the previous equation where both of our variables were on the same side, now the constant in a variable is on one side and our other variables on the other. So when frequency gets bigger, that means energy has to get bigger. So unlike frequency and wavelength, frequency and energy have to be directly proportional to each other. So the larger the frequency of our little bundle of light energy is, the higher its energy is going to be. Now, what would a typical Planck's equation problem look like? What's the energy of a photon from the violet portion of the rainbow if it has a frequency of 7.23 times 10 to the 14th hertz? So it's asking me about energy, so I'm going to get my energy frequency equation. So E equals h times the frequency. And remember, h as a constant, always going to be the same number. And this will be given like the speed of light on the test. So you don't have to memorize it, you just have to know how to use it. And I'm going to multiply that by nu, which is the frequency, 7.23 times 10 to the 14th hertz, or inverse seconds. Now I wrote it as 1 over s because it's easier to see what happens to my units of s. When I take joule seconds and multiply it by 1 over s. S is going to cancel and leave me with units of joule, which is exactly what I expect if I'm getting or calculating an energy. And notice, very small number to 3 sig figs, 4.79 times 10 to the negative 19th joules. Make sure, once again, you can plug these numbers in your calculator and get the right answer. So this is what a typical Planck's constant equation looks like. Now, if I gave you energy, you could then solve for frequency, just like last time we could solve for frequency or wavelength. Here, if you're given one variable, solve for the other. Now, the next idea where we were looking at particles of light energy. So in essence, we were using that same equation that Planck came up with. So Einstein was building on the work of Planck here. And what Einstein was trying to understand is that when light of certain frequency would strike the surface of a metal, then a photoelectron would be emitted. But if light was below a certain frequency or energy, because remember, energy and frequency are directly proportional to each other, a photoelectron would not be emitted. Now, why is that important? Well, a flow of electrons, remember, one photon coming in, if it's a big enough bundle of light energy, would release a photoelectron. So that's a electron. So if we keep hitting it with more and more photons of light, we keep releasing an electron. And what we end up with is then a flow of electrons, which we can harness because flows of electrons are basically what you get when you plug something into the wall outlet. We harness a flow of electrons to turn on lights and to turn on computers and do all kinds of things in everyday life. Well, if we have a photocell in a solar calculator, then if a big enough bundle of light energy comes in and strikes it, it makes a flow of electrons, and therefore the solar calculator will work even though it doesn't really have a battery in it. So Einstein was studying the photoelectric effect, and once he saw the work of Planck, he realized it's about light acting like a particle, because it's kind of like a ping pong ball rolling into a bowling pin. The mass was too different, the size was too different. That little bundle was too big to make our big bundle move. But a large bowling ball coming in, that would knock that pin right over. So photoelectric effect is really treating light as if it is a particle. And like I said, it's what makes solar calculators actually function. So Einstein's explanation then treated light like it was a particle. Unless the incoming light had a high enough frequency or energy, it can't release the photoelectron. So think of it as the stairs. Remember we said that atoms could only absorb energy at very specific amounts? Well, it's because the energies can only exist at certain levels, like a set of stairs. You can't stand in between two steps. You're either going to be on one step or on the other step. So when a bundle of light comes in and strikes that electron and knocks it up, if it doesn't hit it with a big enough bundle to knock it to the top of the steps, then it's simply going to fall back down and it will be as if nothing happened. So a large enough bundle of light would cause this electron to jump up to a high enough energy amount, and therefore a photoelectron. But too small of an energy amount, so basically anything below that energy amount and that frequency isn't going to cause the photoelectron to flow. Anything above would make the photoelectron jump up to that higher step. And that ends our second day of notes for Chapter 5.